So molar mass. We need to be able to know the number of atoms in a sample, and we measure the samples by mass. Why do we need to know the number of atoms? Because chemical reactions, chemical processes happen between individual particles. So if you're going to make water from hydrogen and oxygen, you need 2 hydrogen atoms and 1 oxygen atom. When we get down to it, it's all numbers of particles. They're too small and too numerous for counting, so we weigh them. So you think about, my kids like airsoft, and so you can buy a jar of airsoft pellets, right? And it says it's got like 5,000 in there or something. Do you think they have a machine that counts out 5,000 airsoft pellets? Nah. They know how much one pellet weighs, and so they just fill it up until it has the right mass, and it's good enough, right? They probably throw in a couple extras for those crazy people that are actually going to count them and get upset when they're missing 2, right? They'll give you a couple extras. But we wouldn't count something like that. You count them by weighing. We also use counting units when referring to numbers of objects. The one we're most familiar with is the dozen. What's a dozen? It's 12 things. You can have a dozen of anything, right? You could have a dozen children. You could have a dozen donuts. You could have a dozen countries, anything. It just means 12 things. Another unit is the gross. A gross is a dozen. So that's 144 objects. So like little vials, glass vials that we use in the GC often will come in a gross. It's a dozen. There's another unit we're familiar with, a ream. A ream of paper, 500 pieces. These units mean a number of things. So chemists have their own unit that means a number of things. It's just that the number isn't 12. It's just a little different. It's this number. 6.02214 times 10 to the 23rd. What? Crazy number. Yeah, it's a crazy number. Avogadro's number, yep. There is some, I need to look it up. There's some joke about guacamole and avocado and Avogadro and mole. I just can't remember what it is, but there's a joke in there somewhere. So we often refer to this as the chemist's dozen. Students sometimes have a hard time getting their mind around what the heck is a mole. A mole is not a molecule, although it is the first 4 letters of that same word, but it's a mole. It's not a little animal. It's not a sauce. It has an abbreviation, MOL. I'm like, really? We need an abbreviation for this? But there it is. It's an abbreviation. A mole is the amount of stuff that has this many particles in it. So 1 mole equals this number of things. You could have a mole of pennies or marbles. They'd cover the surface of the earth to a significant depth, but you could, right? It's just a number of things, and that number is called Avogadro's number because Avogadro's experiments led us to this concept. Yep.
Here's a quick question. Particles and atoms, they're like 2 different things, right? Or are they the same?
That's a good question. Particles and atoms, are they the same or different? We use the word particle as a more general term. So when I say particle, I mean atom, ion, or molecule. It's just that smallest atomic level piece.
So when we say find out how many particles we have, are we going to use Avogadro's number? Or
We're going to use Avogadro's number.
Same thing when it says atoms too as well? Like how many atoms? All right.
Yep. So for this word particle, just like for a dozen, I think it said units, or dozen objects, right? What is the object? Well, it's whatever you're looking at, right? Eggs, donuts, whatever. Here, particle, we could use the word object here as well. It's Avogadro's number of whatever it is that we're looking at. Usually molecules or atoms. So 1 mole of anything is Avogadro's number of units of that thing. This is a number you need to memorize. If you don't use the 1,4, I'm fine with that. 6.022 times 10 to the 23rd. You need to know that number. And this is one of the reasons we really need scientific notation on our calculators, because that's a 6 with 23 zeros after it, and you can't put that in decimal form. You have to use scientific notation on your calculator. So how much is a mole? Well, 22. 22 copper pennies, that's a mole of copper. That's a reasonable amount, right? Large enough that we can see it, small enough we can hold it in our hands. So a mole is a reasonable amount of stuff. A mole of water molecules is about a tablespoon of water. So inside a tablespoon of water, there are 6.022 times 10 to the 23rd molecules of water. Is this number exact? No, it's not exact. We know it to more decimal places than that, but for our purposes, we don't need more than really 4 significant figures. How did we get that number? That number came about out of convenience. They said that the value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. So carbon-12 is the isotope of carbon that has 6 protons and 6 neutrons, a mass number of 12. And so they're saying, okay, carbon-12 is what we're referencing. It's stable, it's cheap, it's plentiful. Carbon-12. So if you had exactly 12 grams of pure carbon-12, that would be 1 mole of carbon atoms. So this gives us a relationship between mass and Avogadro's number. So a mole of carbon weighs 12 grams. A mole of carbon atoms is Avogadro's number of atoms. Any questions? When we convert between moles and numbers of atoms, it's very similar to converting between dozens of eggs and numbers of eggs, right? Here we're going to use this factor, a mole of atoms equals 6.022 times 10 to the 23rd atoms. If you're doing molecules, you just write the word molecule in there instead. So this can be right side up or upside down, either way. We're going to use dimensional analysis to tell us what to do here. So a pure silver ring contains 2.8 times 10 to the 22nd silver atoms. How many moles of silver atoms does this contain? We're going to approach this as dimensional analysis. So we've got one number given. That must be where we're starting. 2.80 times 10 to the 22. The unit there is atoms. What do we want to find? We want to find moles. How many moles? So we need to convert this to moles. Well, we know a relationship between moles and atoms. It's Avogadro's number. So this will be just a one-step conversion. 2.80 times 10 to the 22nd atoms times and a line. This tells me I want the unit mole on top, and I want atoms in the bottom, because I want the atoms to cancel. So I don't need to think about, do I multiply, do I divide? The units will tell you. Put the units in there, and then we know that 1 mole is Avogadro's number of atoms. And if you get that backwards, a mole is the chemist's dozen, so 1 dozen would be 12 atoms, right? So the number goes down here. 6.022 times 10 to the 23rd. Now, please do this on your calculator, because if you're using scientific notation wrong, you're going to get the wrong answer. And it's one of those little glitches that'll cause you to lose points and not do well on an exam. So 2.8 EE22. The EE or EXP button on your calculator stands for times 10 to the. And if you're always wanting to put in times 10 and you have problems not doing that, say times 10 to the as you push the EE button. So I've got that in there, and then I go divide by 6.022 EE23. I'm never going to put 10 in there. That's included in the EE button. So 0.4649. How far do I need to go with this? 3 sig figs, right? this number has 3 sig figs. Avogadro's number, as I'm using it here, has 4. So 3 sig figs, there's my third one. I'm going to write down 2 extras because that's what I do. And the unit would be moles. Then I'm going to round 0.0465 moles. If you came up with a really big number, you're using scientific notation wrong. Okay? Please come see me in lab and we can fix that. Yeah?
Would we also put that in scientific notation or no?
You can express this answer in scientific notation, but you don't need to. Sort of my rule of thumb is if I have to get my finger out and count zeros, which I did on some worksheets yesterday, I'm like, it was like 1.55 times 10 to the 8th. And they wrote 155000000. It was the right number of zeros, but I'm like, really? You're making me count your zeros? Okay. I can see that there's 1 0 after the decimal point, so. But scientific notation is never wrong. Any other questions?
Well, it's only wrong when it's wrong.
Well, if you do it wrong, it's wrong. Yeah. Or if they're saying, take this number in scientific notation and write it in decimal form, and you do it in scientific notation, that would be wrong. So counting atoms by weighing them, we need one more thing. We need the mass of 1 mole of atoms. So for carbon, that's 12. For carbon 12, that's 12. But carbon has several other isotopes. And so the atoms, or the elements' atomic mass was in atomic mass units. Because of how Avogadro's number is defined, the element's molar mass in grams per mole is the same number as its atomic mass in atomic mass units. So those numbers on the periodic table under the element symbols are the atomic mass, the average atomic mass in AMUs. They are also the mass of 1 mole of atoms in grams. And that's why Avogadro's number is what it is. So molar mass is the mass of a mole. Has nothing to do with teeth. So 26.98 grams of aluminum. That is the number under aluminum's symbol on the periodic table. That's its molar mass. That's the mass of 1 mole of aluminum. And 1 mole of aluminum is Avogadro's number of aluminum atoms. Here we've got carbon and helium. The reason that this is 12.01 instead of exactly 12 is because carbon 12, although it is the most abundant isotope, there are also carbon-13 and carbon-14. So when you do the average mass, it's a little higher than 12. So here are the relative sizes of these different atoms. We see aluminum is larger and heavier than carbon, and helium is really small. So we're looking here at the same number of atoms, but that same number of atoms of aluminum weighs more than the same number of atoms of helium. So let's say you took, you had 5 pickup trucks and 5 semi-trucks. Same number of trucks, but the 5 semi-trucks weigh a lot more than the 5 pickup trucks. Why? Because each individual piece weighs more. So a mole is always the same number of objects, but the mass is different because those objects have different masses.
So when we're doing our conversions, for example, if we're doing carbon, would we put 12.01 grams of carbon times 1 mole of carbon on the bottom and then Avogadro's number on top, or how that works? Because I know they have to cancel out the grams.
That's a good question. You would use either the grams equals the moles as one factor, or you can use moles equals Avogadro's number of atoms as one factor, or because all of these are equal, you can also go 12 grams, 12.01 grams is equal to this number of atoms. But you always just have 2 pieces of it.
So it is okay to rewrite, like, for example, 12.01 grams on the bottom of your conversion and then 1 mole on top?
Yeah.
Because it feels like it's wrong sometimes if you're writing the same thing on the top, you know?
Yeah, no, it's okay. Let's do a couple of examples, and maybe it'll be a little clearer. So that molar mass, the mass of a mole, is our conversion factor. So for carbon, 12.01 grams is the mass of 1 mole. So we can say that's 12.01 grams of carbon per mole of carbon. And if a question asks you, what's the molar mass of this? You would usually express it with units of grams per mole. It's a vertical fraction, though. It's grams divided by moles. There isn't a number here, but we understand that it's 1 mole. If you're talking about a speed, I'm going 70 miles per hour. That means 70 miles per 1 hour, right? 70 miles in every hour. So this is 12.01 grams in every mole. Or we can turn this upside down and write 1 mole over 12.01 grams. Both of these are good because 12.01 grams is equal to 1 mole for carbon. Does that help at all? So let's calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So 35.8 grams of copper. And we want to know the number of moles. So grams to moles we can do in one step. What we need is the molar mass for copper. So we look at the periodic table. This one says 63.546. 63.546 grams of copper per mole. Or you can say grams of copper equals 1 mole. It's the same thing. So we start with our number here, 35.8 grams of copper. And I'm using my path here. I'm going from grams, come on pointer, grams to moles. So grams to moles, put the moles here. And then I want grams in the bottom, so the grams cancel out. After I get the units in, I put the numbers in. So the number is with gram, because it's always grams per mole. Just like a speed, you're always saying, well, it's 55 miles per hour, or 60 miles per hour. You don't say 1/60th of an hour, or 1 mile per 60th of an hour. What did I say? 1 mile per 60th of an hour. It's always the 1, right? So 1 mole, and then the number goes here. Sometimes the number's in the bottom, sometimes it's in the top. The number goes with grams. So 35.8 divided by 12.01. How many significant figures? Yeah, what am I doing? You guys have to stop me when I do this. 12.01 isn't right. Copper and carbon both start with C, but they're not the same. Good grief. It's this number. Okay. Another reason why you write stuff out. Let's try that again. 35.8 divided by 63.546. Okay, that's better. 0.563. As I'm writing digits down, I want to know when I can stop. This has 3 sig figs. This has 5. So for these molar masses, it is always fine to use whatever is on a decent periodic table that you have available. So this one has more digits. The one on the yellow sheet, I think, only has 4 significant figures. That's fine. If you want to take one like this and round it to 4 significant figures, I'm okay with that. You should always have at least 4 sig figs in your masses, okay? Never round them to whole numbers. Don't do it. So 3 sig figs here and 5, so I need to keep 3 here. There's the 3, write down the next 2 moles, and then I can look at it and see how to round it, 0.563 moles. That would be moles of copper. Any questions? The question is, when are we going to be done with lecture? It's coming. I think we have 2 examples left, maybe. So we've got all the tools now that we need. And so if you need help with a path, it often ends up grams of element to moles of element to numbers of atoms, or going the opposite way, or doing one part. So how many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. And we're given this information. A carat is 0.20 grams because, I mean, who remembers the relationship between carats and grams? Not me. So what do we do here? We read the problem. We write down the numbers. We're just going to use those same problem-solving strategies that I've been trying to teach you. So 1.3 carats. And this is obviously a conversion factor. And what are we trying to find? How many atoms? So we're trying to find atoms of carbon. And so this one's a little trickier. We have to figure out how to get from carats to atoms. Well, this is kind of a clue. We should probably use this. This would allow us to convert carats to what? Carats to grams, right? Because I know that 1 carat is 0.2 grams. So how do I get from grams to atoms? We can use Avogadro's number. Now, we can go directly from grams to atoms, or we can go through moles. I'm going to go through moles because that seems more straightforward for most people, even though it's a little bit longer. I'm going to convert grams to moles using the molar mass of carbon, and then I'm going to convert moles to atoms using Avogadro's number. That's the hard part, figuring out how you're going to do it. If you're getting answers wrong in mastering chemistry, go back and actually write the path out. Okay? It is the key. So I've got my carats, and then I'm going to have a fraction with grams on top, and a fraction with moles on top, and a fraction with atoms on top. Because my path tells me what to do. Carat, gram, mole, atom. Carat, gram, mole, atom. Fill the units in so they cancel out. And down here. Oops. Units first. Now we put the numbers in. Well, this one's written up here for us. 1 carat equals 0.2 grams. So 1 carat, that's this conversion here between grams and carats. So I'm going to put a 1 down here and a 0.20 with the grams. This one at the end is the Avogadro's number 1. A mole is Avogadro's number of atoms. So 1 mole, and this is going to be 6.022 times 10 to the 23rd atoms. In the middle here, this is the molar mass. This is pure carbon, and so we need the molar mass of carbon. We look at the periodic table. 12.01. So 1 mole is 12.01 grams. In the examples I do in lecture, I will usually use 4 sig fig molar masses because I have a lot of them stuck in my head, and it saves time. So then we just go across. 1.3 times 0.2 divided by 12.01 times 6.022 EE23 equals. And my first number has 2 significant figures. This has 2, this has 4, that has 4. So my answer should have 2 significant figures. So there's my 2. I'm going to write down 2 extras. And this is times 10 to the 22nd atoms. Make sure that you understand how your calculator is showing you that number. Because sometimes students overlook the little times 10 to the 22, and that is actually way more important than the 1.3. Because it is a 1.3 atoms. Can you have 1.3 atoms? No, just like you can't have 1.3 people, right? What's a third of a person look like? You're either a person or you're not, right? So that's the number of atoms. Questions?
Can you write 1.3 times 10 to the 22nd carbon atoms?
Yeah, it's carbon atoms. Good to specify, but not absolutely necessary here. Yeah, this is the last one, so hold on. Okay, titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. Well, that's different, right? Okay, so this is more of a problem that we have to think about and solve. So good to write the numbers down. That's always a good place to start. So I've got 2.86 times 10 to the 23rd titanium atoms. And I've got a density given of 4.50 grams. And I want to write that vertically so I recognize that that's a fraction. Had somebody asking me questions and showing me their work last night, and they had the slash, and they were getting things upside down because they weren't seeing that the cubic centimeters is in the denominator. Okay, so we've got that. It's talking about a cube and an edge length. So it might be helpful to draw a picture. So draw a picture of a cube. Doesn't have to be pretty. And the edge length would be L, right? Let's call it L. You could call it X or whatever you want. We want to know the edge length. Well, how does that relate to any of this? This has cubic centimeters in it, right? We could figure out the volume of this titanium. What's the equation for the volume of a cube? The length times the width times the height. So the length cubed. So if we wanted to know what L was, L would be equal to the cube root of the volume. We need to find the volume of titanium in this cube. So we're going to have to convert one of these to volume. This has grams per cubic centimeter. That can be used as a conversion factor. This is a number of atoms, so this is where we should start. So we're going to start here. We're trying to get to volume. What would be a convenient unit? Cubic centimeters. Because this has cubic centimeters in it. So let's find the volume in cubic centimeters. Because it doesn't specify a unit for the edge length, so we can use whichever one is easiest for us. So how do I get from atoms to cubic centimeters? I need Avogadro's number in there, so I can convert atoms to moles. This density gives me the relationship between grams and cubic centimeters. And then the molar mass will give me the relationship between grams and moles. So this is a more involved problem. It requires an equation and some unit converting. There will be problems of this nature on the exam. 2.86 times 10 to the 23rd titanium atoms. I've got 3 fractions. I need 3 arrows. I need 3 arrows. I need 3 fractions. And for moles, I'm going to grams. Moles down there. And then... No. Okay, so I didn't leave myself enough room, so I'm going to move this out of the way. Cubic centimeters and grams. Grams cancel out. So this last term has cubic centimeters and grams in it. That's the units in this density. So 4.50 grams. 4.50 grams per cubic centimeter. per 1 cubic centimeter. Moles and atoms. 1 mole is Avogadro's number of atoms. It's a very long number. In grams per mole, we need that for titanium. It's on the periodic table, 47.867. So this will give us the volume, which is not the final answer, but we need this before we can get the answer. I'm coming up with 5.05, and then I was like, how many of these do I have to write down? 3 sig figs here, and 3 sig figs there, and the others have more. So we need 3 significant figures. I'm going to write down 2 more. This is more important here because this is not the final answer. We're going to use this number. So that's cubic centimeters. That's the volume. If you got a way different answer, you're probably having a scientific notation issue with Avogadro's number. No, not times 10 to the 20. It's just 5.05. And if your calculator's not telling you that, then you need to come see me in lab. Yeah, because you're having a problem with your calculator. Okay, so the length would be the square root of the volume. Sorry, the cube root. The cube root of 5.0518 cubic centimeters. So when we do that, get 1.7158 centimeters. 1.72 centimeters. Any questions? Yeah.
I got 2.24.
Okay.